Hi everyone, we're going to discuss topic modeling and thank you for joining me. My name is Stav. I'm completing my master degree at IDC, specializing on natural language processing. Also, I work at Amenity Analytics as an NLP research engineer. We deal with massive collections of text data in the financial domain, and we build tools to understand text and to provide useful insights. We deal with many NLP tasks, and one of them is topic modeling, and this is what we are going to cover. So the plan for this talk. We will start with an introduction on what is topic modeling and why you might want to do topic modeling. We are going to discuss the topic discovery algorithm. This is the main part of this talk. We're going to discuss topic classification to documents. And we will end with a discussion on what's available for evaluating topic models. So we're going to talk both about theoretical ideas and we're going to see some practical code examples. And there's a companion notebook that goes with this talk. You can check it in my GitHub page. It has more details on the things I'm going to mention, and please feel free. And let's start with an introduction. So let's say that you just came back from a year of traveling and you didn't read any news articles and you have no idea what's going on and you want to find out. So this is what topic modeling does. It extracts the main meaningful topics in a collection of documents, and we want to come up with meaningful and useful topics, and we want to do it in a very large scale for millions of documents. And note that this is all done unsupervised learning. We don't have any labels. We don't know anything about the articles, no categories. We just have a bunch of text, and we want to find some structure in this text that can help us with topic modeling. This is very useful to many natural language processing tasks like summarization and search and so on. So let's see how we can do it. Okay, so this is an overview on the entire algorithm. We are going to present all of the steps, and later we are going to discuss each of the steps. So this is just a walkthrough, and we start with an input text. The first thing we want to do is have some kind of a numerical representation of the sentences. So for these two sentences, I have some kind of a vector representation, and we are going to do it for each of the sentences in the text. Then we are going to do dimensionality reduction. We are going to come up with compact representation for the sentences. The next thing we're going to do is divide the text, the sentences to groups. So here, each group is represented by a different color, and we want different groups to have sentences with some similar content to them. And once we have the groups, we want to come up with the actual topic. We want to summarize each group, and we do it for each of the clusters. So this might be COVID-19, an election, and the third topic is global warming. And this is the output, the list of topics. Okay, so let's start. The first thing we want to do is extract text embeddings. We are going to use BERT. So BERT stands for Bidirectional Encoder Representation from Transformers. It was released in 2018 by Google, and it's quite an enormous leap in NLP research. And BERT provides us with contextualized word representations. So the word contextualize here, it means that for the same word, I might get different vector representation depending on its context, depending on the entire sentence, and the words both from left and right to the word I'm trying to represent. So let's see an example. I have a sentence like, I like apples. My second sentence is, I like Apple MacBooks. So I have the word apple in both of the sentences. Now, if I encode the first sentence using BERT, and I encode the second sentence, then the representation of apple in the first sentence compared to the representation of apple in the second sentence, if I compare them, I see very different vectors that are far apart, and this capture well the different semantic meaning the word apple has in both of the sentences. So this is about word representation. Now for our task, we want to represent sentences and we want to measure sentence similarity. So we are not just dealing with individual words, but with entire sentences. So how can we do it? How can we represent an entire sentence? Let's see one approach. So we feed the entire sentence to BERT. We get some output for each of the tokens. And now, if we want to represent the entire sentence, we average the tokens. Now, I do it for the first sentence, and I also can do it for the second sentence. I get a representation for each of the sentences, and now I can compare them. Unfortunately, this does not work well. It's just unsuitable to be used with common similarity measures. So we need another approach. So how can we represent sentences and compute sentence similarity using BERT? We can take a second approach. We can feed BERT the entire sequence of the two sentences concatenated with some kind of a separator between them. So now we have one long sequence, and we get some representation that is based on the context, on the fact that we have one long sentence. And this actually can work for sentence similarity, but it's just too slow for real-time application. We have a massive overhead because we need to feed BERT with all the possible pairs. So if we have a large collection of sentences, we have to try all the possible pairs, and this is just computationally heavy. So we're going to use Sentence-BERT. Sentence-BERT, it's a modification on a pre-trained BERT network. You can check out the research paper on Sentence-BERT and see the architecture and the training process. But the key idea is that Sentence-BERT provides us with semantically meaningful sentence embeddings. We can use those for similarity measures in large scale. So let's see a benchmark. If I have 10,000 sentences and I want to find the most similar pair, if I do it using BERT with the approach that we just saw, it will take about 65 hours. And if I use Sentence-BERT, it only takes 5 seconds. So this is quite an enormous improvement. So let's see how we do it with Sentence Transformers package. We install the package. We load a pre-trained BERT model. Here we use BERT-based natural language inference min tokens. We use this specific model because it has high performance on the semantic similarity benchmark. We use base and not large because it's way smaller and it has good performance. And we just call encode. And we get a representation for each sentence. This is a vector of size 768. And this is step 1. We now have a sentence representation. Okay, so we have this representation, but it is of high dimension. We have 768 features for each sentence, and it's quite a lot. And in general, in machine learning, high dimensional data can cause trouble. It is known as the curse of dimensionality. So we have to reduce dimension, and there are few techniques for dimensionality reduction. We are going to use UMAP. It is quite similar to TSNE that we commonly use for visualization, and it works well for clustering. So this is the choice. And for the code, we install UMAP learn. We specified the target reduced dimension. And now we have represented each sentence using 10 features and not 768, which is a huge improvement. And this is the second step in the process. Now let's see clustering. Consider that this is our data set. Each point here represents a sentence in the text. And let's say we want to cluster, want to partition this group. If we go with k-means, the traditional clustering approach, then this is the cluster we're going to get. And it's not really intuitive to what we probably had in mind. And the reason is that k-means is looking for spherical or round-shaped clusters. It tries to minimize the total within cluster distance. And also with k-means, we have to specify k, the number of clusters. Usually we don't know in advance what is the target number of clusters. It's something we want to extract from the data. So this is another limitation of this algorithm. And we're going to use instead density-based clustering. So for density-based, we look for packed data points that have nearby neighbors. And we're going to use HDBSCAN. It's an extension of the density-based algorithm. And it also converts the clusters to have some kind of an hierarchy between them. So on this data set, for example, this is an assignment of clusters. So we have these islands of dense points. These are the clusters, the colorful clusters. And the sea of noise points, the sparse points, are considered as noise. Let's see the code. So it's very important for the HDBSCAN to carefully tune its hyperparams. Mean cluster size is very important here, and it impacts the result of the clustering dramatically. So do it carefully, explore different parameters for your task. And once we completed this step, we have the clusters. We can do the summarization. Okay, so we want to summarize the group of sentences. We will start by finding central sentences. By central, we mean the sentences that are most similar to the other sentences in their group. Then we are going to come up with the importance of the words in these sentences. There are many ways to calculate word importance, like TF-IDF or any other metric. And then we're going to extract noun phrases as candidates for the topic name. So let's see an example. This is our sample text that is partitioned to groups using the clustering. Now let's take one cluster, the blue one, and we want to summarize it. So the first thing we're gonna do is find central sentences. So let's say we calculated some score of centrality, and we came up with these two sentences. Now we want to extract the important noun phrases. So these are candidates or representative words in this cluster, and we can choose one of them. And this is the topic of the cluster. So we do this for each of the generated clusters. And this is the last step. Now we have the topics list. Okay, so this was the entire pipeline of the topic discovery. We talked about each of these steps. These are the tools that we use for each step. I hope it should be clear enough. And again, you can check the notebook for more details. Okay, now we're gonna move on to topic classification. It's a different task. And let's see. Okay, so we just came back from the trip. We use topic discovery to understand what's going on in the world. Now that we settled down, we're working as an analyst for some company, and we have to read and sort many news articles and reports and so on. So now we find an article, and we want to understand if it's related to COVID-19 or not, or many other topics. So we want to classify text without training, because the topic of COVID-19 is a topic that I just discovered. I don't have any annotation for this topic, so I can't use the normal pipeline of supervised learning for this task. But I still want to be able to say if this article is related or not to COVID-19 or to election or any other category. So there is a way to do it. It's quite shocking, but we can do it. We can classify to categories that we never seen before. And this is done using zero-shot learning. So I won't go into the internals. Hugging Face has a great blog post. You can find more details on the internals there. Please check the links. But let's see the code example. We specify what is the document, what is the text that we want to classify, and we specify what are the candidate topics. So this is the list that I want to check against. And all we have to do is call the classifier with the document and the topics. And the result is a score, some similarity or relevancy score for each of the topics. So we have the election score, COVID-19, and global warming. It's quite easy to use and it's very powerful. So please check it out. And the last thing we're going to discuss is evaluation methods. Okay, so naturally arises the question of how well our topic model performs. It turns out it's not so easy to answer that question. If I have this data set, so I can assign clusters in many ways. And even if we find two domain experts and ask them which is better, the left assignment or the right assignment, then they might disagree between them which is better. If we get a list of topics, then we might get a disagreement on whether a topic is useful or not. So it's quite hard to decide. There's no objective measure. And in general, clustering is ill-defined and topic modeling are difficult to evaluate. And yet we still want to have some evaluation to our model. And we want to assess how well it performs. So we can come up with some measures, but it really depends on the task. So the quality of clustering or topic modeling, it really depends on how we are going to use it. So we have to be mindful and we have to think of our specific needs, how we're going to use the topics, what we are trying to achieve. And based on that, we can define and measure our own quality measures. So let's see some examples. We can ask ourselves, are the topics understandable? Can we get an interpretation of the topics? So a way to achieve that is human judgment. We can examine our result. We can use some domain expert or annotator and see if it makes sense. For a specific topic, we can see the list of top representative words and we can ask if they are related to each other. This is coherence. We're trying to understand if the words support each other, if they have a similar content to them. Another thing we can examine is whether the topics overlap. So if we have first election and second election and third election, these are all topics in my list. It might not be good for my purpose. So I might want to measure diversity. Also, we can ask if the list of topics that we see, if it really covers the entire set, are we missing anything? So this is coverage. And we can come up with more questions and more ways to quantify these measurements. Now let's see one example of a measurement. This is the coherence. So here we use Gensim. Gensim has a very powerful topic modeling framework. So here we use the coherence model and we want to evaluate two topics. The first one, we give the top representative words. So we have virus and pandemic, vaccine and mutation. The second topic, the representing words are TikTok, Python, and Queen Elizabeth. We specify what is the coherence measure. There are a few possibilities here. Here we use UMass. And we ask the coherence model for the score for each of the topics. So as you can imagine, the first topic will have a high coherence score. These words support each other. The second one will have a lower score. And this is a way to calculate coherence, just out of the box implementation that you can use. And that's it. These are the materials that I use. I really recommend exploring each of them. And thank you for listening. Thank you for your time.